So Onur will now present the story of RowHammer.
Okay, thank you. I'm quite jet lagged, so I hope I will survive this presentation. So I'm going to talk a little bit about RowHammer. This is going to be a high bandwidth talk, summarizing, let's say, the developments over the last 12 years. Clearly, I'm going to skip a lot of slides to be able to do that, but hopefully this will complement Herbert's talk nicely. I also call this, can we be free of bit flips soon? And I don't believe we will be. So I'll start with this. How many people know where this bridge is? Anyone? Yeah, Tacoma Narrow. So a lot of people. This doesn't exist anymore because this is what happened to it. It's a bit flip. It's a reliability, safety, and security problem. And these people are also vulnerable to that effect, let's say. They're constructing New York and they're happy. But if a bit flip happens there, they will not be happy very soon. I like this picture also. This is Mr. Bean being a visionary of self-driving cars. And this is reality today. And if there's a bit flip that happens over here, Mr. Bean will not be very happy either. So what is RowHammer? Essentially, RowHammer is the fact that you have these bit flips in commodity DRAM chips that everybody uses today. At the time we first started doing the research in 2012, we found out more than 80% of the tested chips are vulnerable. Today, all of the chips are vulnerable to this problem. I'm going to show you some more recent data. What's more interesting potentially is, for this audience especially, is that it's a simple hardware failure mechanism that can create a widespread system security vulnerability. And you can see that people are writing somewhat popular articles like this. Forget software, now hackers are exploiting physics. I like that one. So I'm going to give you a quick perspective. So we've been looking at memory errors for a while, and we argued that you should really take a systems perspective to fix these errors as opposed to a device perspective. And to give you a little bit background on DRAM technology, essentially, this is the technology that we use to build our main memories today in almost all computing devices. There are very few devices that don't have DRAM today, and I'm not sure if they will survive. But basically, if you look at DRAM, it stores charge in this capacitor, and you need to have access circuitry, word line, access transistor, bit line, and sense amplifiers. And for this to work, both the charge storage device should work, as well as the access circuit should work, and they both should be reliable. And we've been reducing the size of these structures so that we can store more bits per area. And if you reduce the size of these structures, both of these become more vulnerable. And by the way, this is a logical picture of DRAM. A physical picture looks very, very different because people actually do a lot of tricks to get this to be extremely dense. I'm happy to talk about that, but we don't have time. So essentially, as you reduce the size of the circuit, it becomes less reliable. This is a study that we did with Facebook a long time ago. We analyzed all of the memory errors on all of their servers on the entire world, essentially. There's a lot of memory. They didn't allow us to put how much memory because they were worried about their stock price. Probably they should be worried about some other things about their stock price, but they seem to be doing quite well. But basically, this is a correlation study. We found out that if the DRAM chip, there's a strong correlation between the density of the DRAM chip that's employed in the server and the failure rate that you get in the server, as you can see. Because in denser DRAM chips, you get cells that are smaller and that are closer to each other, so they're much more vulnerable to noise. Okay, if you're interested, you can read more about it. We also wanted to understand this sort of effects in much more detail, so we built FPGA-based memory controllers to test DRAM at large scale. And we've actually open sourced this. This is a lot of the RowHammer studies were done. I'm going to talk about this. This is open source. People have been using it. We'd be happy to help people. And more recently, we released a updated version of this that can test DDR4 chips more flexibly, etc. And you can find our FPGA prototypes. I'm happy to talk about them. So we did a lot of reliability studies and a lot of other studies also. But we also did some studies with Intel initially about RowHammer. So what is RowHammer? Just to give you an idea, if you are a circuit person, there's nothing fundamental here. The fundamental thing is read disturbance, and read disturbance happens in any memory device. The interesting thing here is the read disturbance happens in DRAM, which is employed in everywhere, and this gets exposed directly to software. Essentially, what is the read disturbance in DRAM? You activate a row, which means that you apply high voltage to that word line, or you open it. And then you, in order to read a location in DRAM, you need to do this, basically. In order to read some other location in some other row, you need to deactivate that row, meaning you apply low voltage or precharge it. Now, if you keep doing this repeatedly, activate, precharge, activate, precharge, activate, precharge, activate, precharge, which is a legal access pattern, you get bit flips in some physically adjacent rows. And this is essentially the read disturbance effect. This should not be happening. You get data corruption, and those rows could be belonging to yourself or some other application, to the operating system, anywhere. Clearly, this breaks the memory abstraction as we know it today. And when we first did the studies, as I said, we showed that more than 80% of the chips were vulnerable. And this is a technology scaling problem because chips that are older, you could not do this hammering or activate precharge enough times before the cells get refreshed to induce a bit flip. But as you can see, all of the chips that were manufactured between 2012 and 2013 were vulnerable at the time. So I'm going to update you a little bit more. So why is this happening? I don't want to go into a lot of device details. There are actually a lot of interesting things at the device level as well. But it boils down to DRAM cells being too close to each other and having electrical interference between the wires and the cells. And I like thinking of it as when you activate a row, an adjacent row gets slightly activated as well. It's an abstraction again. Vulnerable cells in that slightly activated row leak a little bit of charge. And if you do this hammering enough times, you leak enough charge that you deplete the charge, assuming the cells do not get refreshed before. Okay, so clearly this is interesting. It's a circuit level failure mechanism. You could put it over here somewhere, but it affects everything else because these errors get directly exposed to the essentially the programs that you write. Okay, when we first did the studies, we actually released this code also, which basically shows that you could induce these bit flips in real devices. What this code does is basically it avoids cache hits, it avoids row hits, such that it ping-pongs activates to DRAM rows X and Y, and hopefully you get bit flips. Now, we also showed that if you actually sandwich one row between X and Y, you get many more bit flips. Later work actually took advantage of that to actually do the double-side hammering, etc. Okay, so this happens in all processors today. We get to today, actually, all processors at the time. And clearly, this breaks memory isolation. And when we wrote the paper, we said that somebody can take advantage of these bit flips to hijack your system, crash it, take over it. We didn't show a proof of concept of it, but these good folks from Google Project Zero showed essentially that, which is interesting. Basically, this is a copy and paste from their blog post and Black Hat presentation. They basically replicated the study. They were able to induce these bit flips on laptops, and they basically use these bit flips to create an attack where they were able to induce, as a user-level process, bit flips in the page table entries of the user-level process that points to the user process's own page table. And they were able to get write access to their own page table as a user-level process, which essentially breaks whatever you can do, whatever after that point, right? And after that point, people have started drawing pictures like this. These are not my pictures, but I like them. And some famous hacker on the internet said RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you're after. I like these kind of nice analogies, let's say. And there are later works developed a lot of interesting RowHammer attacks. Herbert is involved in some of them, certainly. I'm not going to bore you with all of these attacks, but once you have a bit flip, basically, you can exploit it, and this could break all of the security in your system. This is a nice paper I like that basically takes over the Android operating system. You could excite these attacks via GPUs. You could do it over RDMA, remote access. Interestingly, people have shown that even if you cannot take over a system, you could break confidentiality and you could read private data using an attack called RAMBleed. And maybe more recently, people have shown that you could induce these bit flips in neural networks, both accelerators and CPUs, and you could actually get rid of the accuracy to levels that are unacceptable completely in an otherwise reasonably accurate network, essentially. Okay, so people also draw pictures like this. Maybe it's a solution or another problem, let's say. Okay, we've been writing papers about it. I'm not going to again bore you about these, but let me give you some understanding and then what has happened over time, what the industry is doing, and then what's maybe the right thing to do from our perspective going into the future. So we did a lot of studies to understand RowHammer. This is the first paper. I'm going to show you some examples. We keep testing a lot of modules. This is all data, but all of these are fundamental. They remain today. They become worse. So one thing that you can do is actually refresh DRAM more frequently to fix the problem. Because if you refresh more frequently, you cannot do enough activates so that you can induce these bit flips, right? Now, the issue is you need to refresh DRAM a lot more frequently. Even at the time we did these studies initially, if you want to get rid of all of these bit flips, you need to refresh 7x frequently. Okay, we don't want that, I think. So there's another thing that's interesting from many perspectives. Data pattern matters because data pattern affects charge coupling that you have. And in some data patterns, you get an order of magnitude more errors. And there are a lot of other interesting things. One, errors are repeatable. ECC doesn't work very well because you get a lot more errors than simple ECC can prevent. And if you actually want to prevent this with ECC, your ECC needs to be very strong, let's say. Okay, again, I'm not going to bore you with this, but the reason I'm telling you this is because we need to really understand the problem. It's going to get more complex going into the future. I'm going to talk about this paper. It's getting much worse. It has many dimensions. There's depends on temperature, access time, spatial variation, etc. Voltage affects things. And if you do voltage scaling, you may actually become more vulnerable. And HBM, basically no DRAM is not vulnerable. HBM is vulnerable, and HBM is clearly used in many machine learning training tasks today with GPUs. Now, before I go into a little bit more on that, I'm going to talk about solutions. So what kind of solutions do you need? First of all, we need to protect the chips that are out in the field. We need immediate solutions, and we need longer term solutions. Now, I think immediate solutions, we don't have a lot of option. I'm going to talk about that. Longer term, I think we should try to do the right thing. I'm not sure if we're doing the right thing at this point in industry. So this doesn't cover all of the solution approaches, but I'm going to eliminate the first three over here because these are difficult. Building more robust DRAM chips is costly. Error correcting codes is costly. Refresh rate is basically you need to increase refresh rates to unreasonable levels. Physical isolation is difficult to provide and costly. So solutions usually boil down to reactively refreshing or detecting rows that are being hammered and reactively refreshing the victim rows, or proactively throttling the rows that are being hammered, aggressor rows. So, or combinations of this, clear. Unfortunately, there's no good point we're at today where you get good cost, good power, good performance, good complexity, and good security at the same time. We're at a trade-off space. That's the interesting part. So what industry did with immediate solutions, essentially, they increased the memory refresh rates. And I like Apple because they actually cite our paper in their security release over here. But the entire industry did that. They didn't tell how much, probably 2x or so. So our idea initially, which doesn't work with today's RowHammer thresholds that I'm going to mention, is probabilistic. Basically, with low probability, you refresh the adjacent rows when you're closing a row at the memory controller. Now, at the time, it worked, and it's very low cost. I like the solution, but unfortunately, we need to find much better solutions today. So a version of this is implemented in the DRAM chips today. Initially, it was implemented in the memory controller by Intel until DRAM manufacturers said, we have a solution, believe us, and we sold RowHammer. We're going to get to that. So this is actually something like what we envisioned in the BIOS. Well, we didn't want it in the BIOS. We actually wanted it dynamically, transparently to anyone, essentially. But in the BIOS, you could basically pick your RowHammer solution, either 2x refresh or hardware RowHammer protection, and you could pick your probability of refresh if you want. So Intel disabled this for some time. Okay, I'm going to talk about it. But this is an example of an intelligent memory controller, I would say. You have slight intelligence in the memory controller to fix this sort of errors. So this is going to be my argument in the rest of the talk also. We want more intelligent controllers. We want actually potentially software configurable intelligent controllers, patchable intelligent controllers that the software can actually modify in a good way. And we also want good interface, certainly, to that controller. So before I move on, I should say that we're not strangers to this. People have been designing SSDs for a long time, and we've been doing a lot of research on similar errors, redisturbance on SSDs, and SSDs have intelligent controllers. And if you're interested, I'm happy to talk about it. I'm not going to bore you with it. We've been writing a lot of papers on this topic also. I think we need a flash translation layer type of layer between memory and the CPU, but this layer needs to be very lean because we don't have the latencies that are long as in SSDs and DRAM. Okay, so these are two major RowHammer directions that I believe are important. We really need to understand this much better. Unfortunately, many effects are still unknown, like aging, for example. That's a huge issue, I believe. Environmental conditions, memory access patterns, the system design or software design decisions that we make, how do they affect RowHammer? And then we need to actually come up with much better or flexible and efficient RowHammer solutions. I believe co-architecting system and memory is important, and we're going to hopefully talk about that a little bit. Again, I'm going through this relatively quickly. We can discuss this over the next days. Now, let me give you a little bit what's happening in more recently. So we revisited RowHammer in 2020. Well, a bit earlier, but we published the paper in 2020, where we basically showed in a large-scale study that newer DRAM chips are much more vulnerable to RowHammer at the device level. You can actually induce these bit flips after 4,800 activations, double-sided, so it's really 9,600. So the threshold, the number of activations needed to induce a bit flip has reduced by an order of magnitude since we first did the studies. And it's reducing, it's marching down. And again, existing mitigation mechanisms are not effective. Just to give you an idea, this is simulation results of the mitigation mechanisms, but these are real results in terms of the memory technology. And on the x-axis, you see the number of activations required to induce the first bit flip. You can see that from DDR3 old generation to the newest generation, we're marching from left to right. And this is the performance impact that's caused by different mitigation mechanisms. This is increasing the refresh rate. You can see that it's not going to work. Terra, which is our original solution, is not going to work. So we really need solutions that actually bridge that gap between the solutions we have and the ideal. Okay, let me give you what's difficult. So developing a solution is difficult because we do not completely understand what's going on. So if you really want to protect, for example, against RowHammer, you can figure out what is the vulnerability, how many activations are needed to induce a bit flip, and you can basically refresh the victim rows, for example. You can keep track of the activations that you have, for example, for a given row, and refresh the victim rows before you do that many activations. Now, the problem is that number of activations depends on many factors. So temperature, aggressor row active time, and victim DRAM cell's physical location. So you really need to test DRAM rigorously to find the worst case or add a lot of margin. Again, I won't bore you with a lot of detail. Temperature is something we don't understand very well because you don't have a nice curve. Basically, different cells have different vulnerability in terms of temperature. I'm going to talk about this active for a longer time. I'm going to talk, but I think the certain physical regions of DRAM is also important. Now, what is the problem? Basically, if you don't take into account one of these factors, you may actually have a solution. The solution may work under some condition, but if that condition is violated, if your assumption is violated, for example, if you assume that row A is active for some period of time, and if the row A is actually active for longer, your activation count to induce a bit flip may reduce significantly, and your solution doesn't work anymore. You have not configured your mechanism very well. So this could be used by the defender. This could also be used by the attacker, by the way. You could actually take both hats. I think this is actually an interesting direction to explore. There's a lot of difference between the vulnerability of the cells in a DRAM chip. Some cells are a lot more vulnerable than a majority of the cells. And if you actually focus your mitigation mechanisms for those cells and do a less, let's say, aggressive mitigation mechanism for the other cells, you can actually do better. Okay, so there's more RowHammer analysis. I'm going to skip this one. Voltage is actually important, but unfortunately, there's no silver bullet here. You do a lot of studies, and in the end, you find that there's no silver bullet. That's another thing. HBM chip is actually very interesting, and we're examining more of this. I'd be happy to talk about this more. Let me talk about solutions. This is work we did with Herbert's group to basically show that what DRAM manufacturers did in their DRAM chips were not working. Essentially, industry adapted this target row refresh mechanism, and they didn't actually specify what they did internally. So using our FPGA infrastructure as well as real system results, we showed that you could actually induce these bit flips by reverse engineering what's going on in the DRAM chip. And this essentially the key idea in this work is to hammer more rows than the internal mitigation mechanism that's employed in the DRAM chips can track, such that you overflow those tables that are in the internal mitigation mechanisms and you induce bit flips. Basically, internal mitigation mechanisms are not secure. Okay. So essentially, what the industry took the solution of security by obscurity. Actually, we uncovered a lot more. You could actually reverse engineer all of these chips. If you actually dedicate more effort, you could actually reverse engineer many, many things. But again, I'm not going to bore you with this. You can actually find out what's really going on inside the DRAM chip, even though this is not exposed outside. So industry also has been developing attacks, especially Google and Microsoft have been quite prolific in terms of developing new RowHammer attacks. These folks at Google showed something really interesting. I'm going to mention this quickly because this also shows that your solution can be an attack itself. So what Google showed was that you could hammer one row, aggressor row, a lot, very heavily, and then you could hammer another aggressor row very little. This would cause bit flips in this victim row. This is called blast radius effect, which we have examined. But what's interesting about here is if you hammer this row aggressively, your RowHammer mitigation mechanism may actually refresh this row, and those refreshes can actually be an attack for the other victim row. So essentially, you need to be careful about how you actually solve the problem as well. So they published a paper at Unix Security. So solutions are interesting. Again, I will cover this. So there are many, many different dimensions over here. One is the solutions need to scale with worsening RowHammer vulnerability, and this is getting much worse. And they need to be compatible with commodity DRAM chips as much as possible if you don't want to, let's say, disrupt the industry significantly. Unfortunately, I think I'm going to take an issue with this later on. Scalability, we need to definitely satisfy, but we really need to revisit the interface between processor and DRAM going forward. So this was our solution that tried to satisfy these requirements. This also doesn't work if you actually go to very low RowHammer thresholds, like if you get a bit flip after 200 activations, for example, this doesn't work. So we want solutions that would actually solve the bit flips after 200 activations. So the idea over here is we use Bloom filters to keep track of activations, and we blacklist some rows that are that the Bloom filters tell us have been hammered aggressively, and we throttle accesses to them such that you don't access them to induce a bit flip later on. And I think there's another interesting thing over here. You could actually use these counters to inform the operating system or the virtualization software about a possible attack, and they can take mitigation actions. So this is another even more intelligent controller, as you see, that tries to provide this robustness in the air. So you could say, okay, these are maybe fancy academic papers, but finally, industry admitted the problem. This is ISSCC, the Major Circuits Conference. This is a paper from SK Hynix. This is the first paper that admits the RowHammer problem. You can see so RowHammer somewhere over here. Basically, they admit that the problem exists, and they talk about solutions. Some of them are variants of what we have proposed. The question is this going to be secure? So what they did is essentially inside the DRAM chip, they added an intelligent controller. They have these row activation counters on a per row basis, and they have some logic to refresh the victim rows, which is similar to what people have been talking about. Unfortunately, of course, it's still they don't really disclose exactly how they do it. We'll see how vulnerable this is going into the future. And Samsung, of course, seeing SK Hynix's paper, they had to also release a paper and archive. This is much harder to read, but it has somewhat similar solutions, somewhat probabilistic, as you can see. Okay, so the question is, of course, are we free of these RowHammer bit flips? I don't believe so. And then there's also the question of what else may be lurking. So let me talk about a paper that we published this June at ISCA. We call it RowPress. And the idea here is, essentially, it's a new redisturbance phenomenon. I'm going to tell you why we believe it's a new redisturbance phenomenon that causes bit flips. It also amplifies RowHammer. It's different from RowHammer. And we demonstrated using a user-level program and a real Intel system, we could get bit flips that you couldn't get otherwise with RowHammer protections. And we provide some effective solutions, which I'm happy to talk about. So basically, the idea is normally RowHammer attacks activate a row very frequently. They basically close the row. There's a minimum open time that you have in the memory controller, and you can, memory controller should close the row, can close the row after that minimum time. And normally you maximize the activation count to get bit flips. In this work, we show that if you actually keep the row open for a longer time, like 7.8 microseconds, which is actually allowed by the standard, you get much fewer activations to induce bit flips. And if your RowHammer attack is configured to prevent bit flips after, let's say, 30,000 activations, now you get lots of bit flips in your system. In fact, in some let's say extreme cases, if you're able to keep the row open for 30 milliseconds, only one activation can induce bit flips in adjacent rows. This is scary to me. Okay, so basically we show that we can significantly amplify redisturbance, and it has a different underlying mechanism. The reason it's different from RowHammer is its characteristics are completely different. So the bit flips you get, if you have a Venn diagram of RowHammer versus RowPress, they actually overlap very little, essentially. These are different cells that are affected. And also with temperature, this affects get much worse. I didn't give you exactly how much you can amplify, but you can reduce the activation, you can reduce the number of activations you need to induce bit flips by 1 to 2 orders of magnitude. So if you're at 4,800, you can easily get to 480 or 500. Okay, so the question is, does this happen in real life? And we actually developed a proof of concept, which we hope security researchers will take further. In this proof of concept, we basically essentially wrote a program that would keep accessing different cache blocks in the same row. And with the memory controller, open page policies in memory controllers, you could actually, the memory controller keeps the row open for a longer time. And we showed that you can actually get bit flips in real systems if you access more cache blocks than some number at some point, where you cannot get bit flips with RowHammer. Okay, so how do you solve this? You need to adapt solutions to RowHammer to this, and there are many other solutions, but I'm not going to talk about the solutions over here, which is interesting. Okay, I believe there's more to come. So we're scratching the surface. There are more effects, and there are also other things that we have not examined, like aging, which I am happy to talk about. So I think generalizing what I said, we really need to understand bit flips. And this is not just related to memory. This is also in processors, accelerators, and these bit flips are going to be everywhere. Google and Facebook have written papers about bit flips in processors. They're very worried about these silent data corruptions. I think they're going to be even more worried going into the future. And we need to really understand all of those effects going forward and model them somehow and solve them somehow. I don't think we have great solutions to all of these yet. Let me give you an idea very quickly. Basically, I think we really need to rethink the interface between DRAM and processor. This is unfortunately an area where people are not really comfortable making changes a lot for various reasons. But one idea is actually giving some more flexibility to the DRAM to fix these issues. So if the DRAM actually has some more ability to say, memory controller, I'm maintaining myself, so I'm refreshing myself, I'm doing some RowHammer protection, you cannot issue a request to me. That actually solves a lot of the issues. That actually decouples. I think that's a clean partitioning of the duties across the stack, across DRAM and the memory controller. And we've shown this. We've shown that this can be actually implemented with very little cost. And it actually has a lot of other benefits, like it could improve refresh, RowHammer protection, memory scrubbing, many other maintenance functions that we have in DRAM. I think we need to get to a better separation of concerns between DRAM and memory controller. Because these protections, whenever you change the interface for a single thing like memory scrubbing or RowHammer, it takes it currently takes 5 to 10 years to actually go to a different DRAM standard. But if you actually have an interface that's more flexible, you don't need to change the DRAM standard except for this change that you do initially. Okay. So future, going back to these bridges, this was Galloping Gertie, Tacoma Narrows Bridge. People have been building bridges for thousands of years, and we haven't figured it out. I don't think we're going to figure out how to build computers perfectly reliably. We need to figure out how to live with them and how to actually make them work at the system level. So unfortunately, this is on Seoul, Han River. These are actually incidents with fatalities. This is Minneapolis, this is Genoa, and this is close to my heart in Pittsburgh more recently. This didn't have a fatality, that's the good part. But basically, we're building infrastructure that's much more important than bridges, in my opinion. Computing infrastructure is actually everywhere. And maybe bridges are not important anymore in the grand scheme of things. I believe we need to figure out how to avoid such failures. I believe intelligence in the memory actually is important. Intelligence in memory can actually bring other things. So it's synergistic with doing computation in memory also, which I think is actually the right direction in terms of energy efficiency and sustainability as well. Okay, maybe very quickly, I will mention that none of this is new in a sense, right? This is a paper that these folks from Princeton wrote to attack a virtual machine in 2003. And by inducing memory errors, the way they induce memory errors is actually using this lamp, which is not very controllable, but they did actually. And they were able to take over the Java virtual machine. Essentially, RowHammer replaced that lamp with load store instructions. That's the way I see it. And once you have a bit flip, you have problems. So I will acknowledge my students since they all did the work and I'm talking about it. You can take a look at their pictures over here. And I'm happy to take any questions at this point. Thank you.
Thank you, Onur. So I think after Herbert, you finished to scare us. And so we have, while we set up the next talk, please ask a few questions if you have.
Yeah, Onur, so two quick questions. One really quick. How did you find road crash? Was that just a fluke or was that something that you were looking for?
So we actually in an earlier work, we looked at keeping the row open for a small amount of time, like 200 nanoseconds or so, which is more than 36 nanoseconds. And we saw an increase in the bit flips. We thought these were RowHammer bit flips. We didn't analyze them in that detail. So we took clue out of that and actually extended the interval where we kept the row open and did a lot more rigorous analysis in terms of temperature, in terms of bit flip overlap with the RowHammer. And we figured out that it was a different mechanism. Now, actually, industry is aware of this, but they kind of keep it hush-hush. So there are some patents from Micron that talk about this as Rasclobber. So we found out that about that also, but they don't really talk about the details, but they understand that this is actually a different mechanism than RowHammer.
Interesting. So the other question I had was, what do you think of the new developments in JDAC on RowHammer?
New as of like 2023 or new as of 2021?
23, I guess.
Okay, I think it's great. People are actually openly discussing, and you can see that they're writing papers about it. The openness, like a little bit more openness, is good, but I'm not sure if the solutions that are really proposed, like hiding everything under DRAM without changing the interface in a better way, is the best solution. So I think some of the intentions are good, but I'm not sure if the result will be solving a lot of other problems that we may see into the future as well.
Great talk. Herb's talk was all about abstractions necessary but considered harmful. I mean, here this is actually talk about the lack of abstractions rather than having too many abstractions. And I see where you're going with respect to having better coordination between memory controls and DRAM, but you have not talked about any of the other abstractions of a memory system, in particular the notion of pages and TLBs that basically are a mechanism to protect access to portions of memory, assuming we could reason about pages within DRAM.
Yeah, so that's a great question. I mean, frankly, I don't think we should really expose these errors to that level. I think it's going to be meaning, should the operating system be dealing with these bit flips, protecting them? In my opinion, this should really be handled before that point. That's why I didn't talk about those levels. I think memory should still give the abstraction that there's isolation between the pages, for example, isolation between different memory locations.
Yeah, okay, but But if I may, sorry.
Sure. Yeah, go ahead.
So if you think about the issue of side channel attacks on CPU, right? The consequence is basically we need to partition systems so that it's the end of the SMT era, where anything can run anywhere, including the kernel, right? We're moving into sort of these message passing style models where we dedicate not only threads, but entire cores or groups of cores for a particular application or VM or whatever for extensive periods of time to avoid side channel attacks. In a way, right, the same could be said about memory, is that memory, even though it may be part of a global system, has to be partitioned in a way that is protected from these inevitable side channel attacks, because RowHammer is a form of a side channel attack, depending on how you look at it.
I mean, we can talk about this more, but I don't see RowHammer as a side channel attack, frankly. There's side channel aspects to it, but it's really a memory corruption or fault attack in the end. And maybe it should be treated a little bit differently from side channels, in my opinion. And also, I think there are other issues, like if you have a very large scale memory system, maybe there are some partitioning that you can do, certainly across applications. But then you could also argue that within an application, you don't want these errors as well, right? So it's not just a security issue, it's also a robustness, safety, and reliability issue. So that's why I think that RowHammer should be solved before they get exposed to the system. But some of the solutions that we actually employ for side channels can benefit these cross-application issues. But we can discuss more.